Lecture 3.3 Review of Atomic Physics. Our aim is to measure the abundance of elements in the sun by analyzing patterns of absorption lines. And the game that we play is to try to match up these patterns of absorption lines with known spectra of different elements. So you could go into the laboratory and heat up gases with different elements in them and see what kinds of emission lines you get, or you could try to predict it theoretically. We'll look at the theoretical prediction for hydrogen because it's particularly simple. We can use the Bohr model of the atom. So in the Bohr model, we have an electron orbiting a nucleus with charge Z times E. So E is the fundamental charge, and Z is going to be, how many protons we have in the nucleus. So for hydrogen, Z would be 1, helium, Z would be 2, and so on. Bohr's assumption was that the electron orbits around the nucleus as a little planet orbits the sun, but that we only have discrete orbits because the angular momentum, MVR, is quantized, meaning it's equal to some quantum number n times h bar, Planck's constant. So this is the assumption that Bohr made, and if y'all have taken modern physics, you kind of know the backstory on that. When you put these two things together and just use the electrostatic force between a charged nucleus and the charged electron, you can derive that the allowed orbits follow this relationship. So the allowed orbits are a constant, which is called the Bohr radius, divided by that nuclear charge Z times some quantum number n squared. A naught, the Bohr radius, is equal to about a half an angstrom, and an angstrom is a tenth of a nanometer. So one angstrom is 10 to the negative 10th meters, whereas a nanometer is 10 to the negative 9th meters. So the Bohr radius is 0.05 nanometers approximately. The energy levels associated, or the total energies associated with each of these orbits, scales as 1 over n squared, where n is the quantum number, Z again is the nuclear charge, and E naught is a constant equal to about 13.6 electron volts. We can plot this information on an energy level diagram. So here's the ground state down here. This is the n equals 1 state, and again it has an energy of minus 13.6 electron volts, assuming this is hydrogen and we plug in 1 for Z. In the n equals 2 state, we take basically 13.6 and divide it by 2 squared, or 4. We get minus 3.4 electron volts. The second excited state is the E3 state. You get this, and the lines kind of crowd together more and more and more. In the limit that n goes to infinity, the energy goes to 0. So energy 0 is kind of that limiting case up here. If you give the electron more energy than that, the atom will become ionized, as we'll see later on. So if an electron makes transitions between different allowed orbits, then light will be either emitted or absorbed. And the wavelength, or the frequency of that light, just depends on the difference, or it's just equal to the difference of the energy levels. So for example, suppose you have an electron in an upper state. We'll say that the energy of the state is, we'll call it E upper, and if the electron jumps down to a lower state with energy E lower, it'll radiate some photon. The symbol that we usually use to characterize photons is gamma. When this happens, we will see a single emission line with whatever frequency we get just from this simple formula. So you just take the difference in the energies divided by Planck's constant, and that'll give you the frequency of the radiation that comes out. On the other hand, the inverse process is that if the electron is sitting in the ground state, a photon with just the right energy comes along, the atom or the electron can absorb that energy and it'll get kicked up to the upper state, and what you'll see is an absorption line. Let's look at what the wavelength is for hydrogen specifically. So again, we start with the same equation. H nu, the energy of the photon, is just the difference in energy of our two levels. We know that the energy of a level is that constant E naught times the nuclear charge squared divided by the quantum number squared. We have it for two levels, so we just subtract those two energies. We'll factor the negative sign back inside. That switches the order of these two, and then solve for lambda, so we kind of flip it upside down. So we get that the wavelength is this constant hc over E naught over z squared times this. If we plug in the result that we had before, the hc is 1240 electron volt nanometers, divide that by E naught, which is 13.6, we get this result. So the wavelength of the light emitted is 91.16 nanometers over the nuclear charge squared times this expression. So pretty simple formula. Let's use it to calculate the wavelength of light when electron transitions between the ground state and the first excited state, or the n equals 1 to 2 levels. So there we go. Plug in z is 1, plug in the lower state is 1, the upper state is 2, calculate it, and you get 121.6 nanometers. So, which is in the ultraviolet. So if a hydrogen atom had an electron sitting in the first excited state, it goes down to the ground state, it's going to emit an ultraviolet photon. Spectroscopists typically characterize or lump these transitions into different groups or series. So anytime you have a transition from a higher state to the n equals 2 level, or the n equals 2 level to a higher state, that's called the Balmer series. In each case, the lower state is equal to n equals 2, so we can just plug in 2 for n lower. If we look at the wavelengths of the first three transitions, we get one that's in the red, 46 is kind of turquoise, 434 is kind of in the violet or the blue area. If you go beyond that, the next one, H delta, actually falls in the ultraviolet part of the spectrum. And then if you take the limiting case, where you had an electron very far up, like close to n equals infinity, and it transitions down. If you plug in infinity for the upper state, 1 over infinity is a 0. So you get 91.16 divided by 4, well, times 4 because it's to the negative 1 power. You get 364.6. So that's called the Balmer limit, which is the shortest, the limiting case of the shortest wavelength light that results when you're transitioning to the n equals 2 level. Okay, so if you look at a spectra of all this, so in our little diagram here, we've got wavelength increasing to the right in nanometers. So 656 nanometers is right here. That's H alpha. This one is H beta, H gamma, H delta, and then there's the Balmer limit right there, where all the lines are kind of piling up on each other. So again, the visible part of the spectrum only catches those first three lines. All the others are out in the ultraviolet. If we look at transitions to the ground state, then you can kind of immediately see that the energy gap here is a lot bigger than in the Balmer series. So all of these photons are going to have more energy and therefore shorter wavelengths. So all of these are going to be out in the ultraviolet part of the spectrum. The lower energy state is going to be 1, so we just have 1 minus whatever the upper state is. You plug in some examples, and again, you see all of these transitions are out in the ultraviolet. The Lyman limit is what you get when you plug in n equals infinity for that upper state. And so the Lyman limit is the shortest possible transition that you can have in the hydrogen atom. If you go the other way, so if you're lower state is now moved up to the n equals 3 state, you see all these arrows are now shorter, so they're going to have longer wavelengths. These are all out in the infrared part of the spectrum. So that series is all out here. So again, here's the Balmer series here, there's the Lyman series, here's the Paschen series. There's an infinite number of other series, right, as you go higher and higher up in the energy levels. But these are the three that you tend to see the most in astronomy. One more thing that we need to talk about that has to do with the structure of atoms before we talk about spectral lines in more detail is the degeneracy of atomic energy levels. So the degeneracy means how many quantum states do you have that have the same energy. You might remember from some class in atomic physics that for every energy level, you can have different angular momentum states. So an s orbital has an angular momentum of 0, a p orbital, a d orbital, these other orbitals have higher angular momentum values. And again, this is a result of quantum, but it turns out that the number of possible quantum states for any given energy level goes as 2n squared. So when you're in the ground state, you can have an electron that has a spin up state or a spin down state relative to the proton, and those are the two states that you get. So that's where the 2 comes from. In the n equals 2 state, you get 2 times 2 squared, so that's a total of 8 states, and then 18. Anyway, that's the degeneracy of the energy level. When we apply it, we'll be calling that the statistical weight in the future calculation. So you can it's the same thing. Statistical weight, degeneracy of a level, it means the same thing. Okay. So let's now, there's a bunch of atomic processes that are relevant to astronomy. Generally speaking, the first 2 sets of atomic processes have to do with exciting an electron to an upper state or having that electron decay back down to a lower state. That's this first group. The second group has to do with ionization of atoms. So we're going to go through all these fairly quickly and look at all the possible things that can happen to atoms. In a cold environment with no radiation, no other atoms around, if you just had a single isolated atom, it wants to settle down into the lowest energy state possible. And in order for an electron to be excited up into one of those excited states that we've just been talking about, you need some energy to kind of lift it up into that excited state. So generally speaking, that can happen in 2 ways. The first way is called photoexcitation, where an atom absorbs a photon with just the right amount of energy to kick the electron up into an excited state. So in the diagram, we see a neutral atom, a passing photon given by the Greek letter gamma. When the atom absorbs the photon, the atom is kicked up to the higher state. We can express this reaction using this simple equation. X will represent some atom in the ground state. Gamma is the passing photon. And when the photon and the atom come together, the atom is raised to an excited state, and that's designated by the asterisk. So X star means that the atom is in an excited state. Energetically, what's going on is very simple. It's just that the energy of the photon, h nu, is equal to the difference in energy levels in the atom, delta E. The other way that you can excite an atom is through collisions. So in collisional excitation, you have a particle bumps into your atom, and it transfers some of its kinetic energy into the atom to lift it up into that excited state. So often, like say, for example, in the atmosphere of the sun, there's a lot of free electrons flying around because it's hot. And so maybe one of those free electrons might bump into the hydrogen atom, or it might be another hydrogen atom that bumps into it that that would excite it. This could be a number, any particle at all would work in this process. So we could say that our initial atom, say plus an electron or any other particle, leads to an excited state, and then you still have that initial particle left over. It's just going to have less kinetic energy than when it started out. So the energy balance equation says that the energy difference in the excited state compared to the initial state, that delta E, is just got to be the difference in kinetic energies of the electron before and after the collision. The opposite process of excitation is called de-excitation, and you can do that in 3 ways. So the first way is called spontaneous emission. So here, an electron in the excited state simply jumps back down to the lower state all by itself, spontaneously. So you have an excited atom, X star, and it decays down to an atom in its ground state plus a free photon, or plus a photon. And the energy of that photon is just simply equal to the energy difference in these energy levels. So it's exactly the process in reverse that we just talked about. Another way to de-excite an atom, it was discovered by Einstein. And in this process, a photon with just the right energy comes passing by the excited atom, and it triggers it, or it stimulates the atom to decay slightly more quickly than if it was just left alone. So here's what it looks like. You have an excited atom, a photon comes passing by, you get an atom in the ground state, and then you get 2 photons as a result. Now, it turns out that the wavelength of the passing photon has to equal exactly the wavelength of the photon that's going to be emitted in the emission process. So in other words, the energy of this guy has got to be equal to delta E, the energy between these 2 states. So the energy balance equation is very simple. We simply have that the energy of the emitted photon is equal to the energy difference between the energy levels. So same as what we had up here. So the third way to bring an electron back down is through collisional de-excitation. So here you have a passing particle. It could be a free electron or another atom. This passing particle bumps into it, and that triggers the atom to de-excite into, say, the ground state. So again, we've got an excited state plus some passing particle leads to the neutral state. And now what's happening is that you're not emitting a photon anymore. What's happening is that particle that's coming by is carrying away the extra energy that was kind of stored in potential energy here in the atom. So this electron is going to have more energy than it started out. And the way that you can see that is here. So again, the energy level difference is just equals the difference in kinetic energies of that colliding particle. Okay, so let's do a little example. Let's find the velocity that you would need an electron to have to collisionally excite a hydrogen atom from the ground state to the first excited state. So the energy difference between the n equals 1 and n equals 2 states is just given by this. So, that's the energy of the second state minus the energy of the first state. And you plug all that in, you get 10.2 electron volts. This energy must equal the kinetic energy of the electron. So you set the kinetic energy equal to 10.2 electron volts. So we set kinetic energy as 1/2 mv squared, solve for the velocity. So you plug in the kinetic energy, 10.2 electron volts, and now we have to convert electron volts into joules. So we multiply by the conversion factor of 1.6 times 10 to the negative 19th joules per electron volt to get everything in MKS units. So we find that the velocity of the electron must be at least 1.89 million meters per second. So that's about half of 1% of the speed of light. And I should say, this is the minimum velocity needed. You could have an electron going faster than this and only transfer some of its kinetic energy into the hydrogen atom to excite it. So this would be the minimum velocity required to collisionally excite it. Okay, so we've been talking about excitation and de-excitation. The second set of processes is called ionization and recombination. So ionization is a process of removing electrons from an atom. The ionization state in astronomy is represented by Roman numerals. So let's look at examples. Neutral anything is given by the Roman numeral 1. So neutral hydrogen is called H1 for short. If you ionize hydrogen, you only have a proton left. That's called H2. So as you increase the Roman numerals, you go to higher and higher ionization states. So, for example, if you had neutral helium, that would be helium-1. Singly ionized helium would be helium-2. Doubly ionized helium would be helium-3. The ionization potential is the minimum energy you need to remove an electron from the atom. So if you have an electron that's in its ground state, the energy would be minus 13.6 electron volts. You would need to give the atom 13.6 electron volts to bring it up to 0. So the ionization potential for hydrogen is 13.6 electron volts. It's just negative the ground state energy. So here's a table showing ionization potentials for different starting ionization states for some elements. So hydrogen, we just saw, has ionization potential of about 13.6 electron volts. As you go down this first column, this is how much energy you need to ionize neutral helium, neutral lithium, neutral beryllium, all the way down. So you need more energy to ionize helium because it's a noble gas, it's tightly bound. Lithium, though, that valence electron is barely hanging on. It only takes about 5.4 electron volts to ionize it. As you go along this diagonal, these diagonal ones are, you have a single electron bound onto a nucleus with no other electrons present in the atom. So helium-2 means singly ionized helium. That means you've got one electron removed and one remaining. So it takes 54 electron volts to ionize already singly ionized helium. It takes 122 electron volts to ionize doubly ionized lithium, so that you would only be left with, a bare nucleus. So you can see you need more and more energy to completely strip away that last remaining electron as you go down the periodic table. Okay, so there are a couple different ways to do ionization. One is through photon. So photoionization occurs when a photon comes along with sufficient energy to completely remove the electron from the atom. So afterwards, you get just in this case, you would have a bare proton left over and then a free electron. So we say that you start off with your element, a photon comes along. Now H plus, the plus indicates that we are singly ionized in this case, and then we have an electron left over. Then we have a free electron there. Energetically, it looks like this. So if this is the energy of the photon that comes along, that total energy of the photon is going to be shared between what it takes to rip the electron off of the atom, that's the ionization potential, and whatever energy is left over will go into the kinetic energy of the free electron. You can also have collisional ionization, just like we had collisional excitation. So here we have another particle bumps into our atom, ionizing it. And so now we'll have our particle plus the electron that was held on to the atom. So we could write this as the atom plus our particle gives an ionized atom, and then we'll have two particles. We'll have the electron that used to be bound on, and then assuming that our colliding particle is also an electron, we'll have two electrons left over. Energetically, it looks like this. The energy of that colliding particle, that's this, will be divided into the ionization potential, how much energy it costs to rip the electron off the atom, plus the kinetic energy of the electron that was bound to the atom, plus the kinetic energy of that colliding particle. Recombination is the inverse process. So recombination is when you have an ion, when it meets up with a free electron, they get together and form an atom plus a photon. So the energy state looks like this. You start with an ion, X plus. A free electron comes along. They get together to form a neutral atom, say, and then you get that photon left over. Energetically, kinetic energy of the free electron plus the ionization potential will equal the energy of that photon as it goes off. So what happens is that when we have a passing electron, it's got a kinetic energy given by this arrow right here. When it recombines with this ion, it will jump down to the ground state. That energy difference is going to be carried off or emitted by the photon. So this energy difference is going to be h nu. This distance right here is 1/2 mv squared, and this is the ionization potential. So h nu, that total energy, is going to come from the kinetic energy of the original electron plus the ionization potential that's released when it recombines with the atom. Okay, so here's a homework problem. Okay, so we can kind of draw a little diagram. We have a free electron coming along with a certain amount of kinetic energy. It bumps into a sodium atom that has an electron that's in its ground state with ionization potential of 5.1 electron volts. And so after this electron ionizes the sodium atom, we'll have two electrons left over, one the original electron and the other one was the electron that was bound to the sodium atom. And we're going to assume that both of them have zero energy after this process. So they both just this guy has just barely enough energy to ionize the sodium atom. So they have, each electron has zero energy left over after they're now free. So what you want to do is, calculate the minimum speed of this electron to just barely collisionally ionize the sodium atom. All right, in the next lecture, we will talk about spectral line strengths.